This will be a short lecture because it's not fair to give you a bunch of new material and then test you on Thursday how well you remember it. So it's maybe 30 minutes or so. Ask me anything type of a lecture, a quick review of the things that we have done, and off we go. You can fill out the course surveys. Yeah. What we did in the last lecture on Thursday is we put a lot of things together. We have talked about DLLs and showed how they're used for phase alignment and deskewing in modern SoCs. Then when we really don't have an option to do the deskewing, modern SoCs go globally asynchronous, locally synchronous, which means that there is a PLL that generates a clock for each of the tiles or cores or whatever the units there of the synchronous world are in those cores, in those SoCs. And then they go through asynchronous clock crossings between the tiles. Those can be, what we need to do for single signals is to make sure that we don't run into metastability, and we've talked about that a bit. There is a calculation that goes with that. We didn't cover that, but you can totally do it. And there is a, there are asynchronous FIFOs that typically manage the communication and rate adaptivity between domains. Then we talked about supplier regulators and talked about those that can be and those that are a little harder to integrate on chip. That's a hot area of research, and there has been quite a bit of activity that has even early startups succeeded in productizing regulators. So things that are interesting. So what was there is, we have linear regulators that are inefficient but can be integrated, and we have switch capacitor regulators that are a lot more efficient. Switch inductor regulators are a lot more efficient, but are very difficult to integrate because we need magnetic components and they just don't naturally grow on silicon. And then there are switch caps that are in between, and they are very noisy too when somebody needs to deal with that. And then we talked about this, problem of the whole 251 coming down on you in the case of supply groups, and how we need to deal with that. In every SoC needs to be power managed. Anything that is larger than a tiny thing needs to be power managed, and supply groups happen. So you need to detect it and slow down the clock. So we have a final on Thursday. It is not incredibly difficult final. It's like 4 quizzes in a row. You just need to keep it together for about 80 minutes. And go knock them down one after another, right? And if something doesn't sound, calculation should be relatively simple. It should be something that if you have followed all the lectures, you should be able to do it. If you have not followed, if you missed about a half of the lectures, then it may be dicey. But if you have been with us, it should be something that is very familiar. Then we have project presentations next Thursday from 9 to 12:30. They'll be in PWC, and we're going to keep it strict to 12 minutes per individual or team, and 3 minutes for Q&A because we need to get through everything there. In 12 minutes. How many slides should you present? 20, 30? No. What's a good number? 12, I would say 10. And rehearse beforehand, right? So regarding the slides, what's a good rule of thumb? Or how long should the slide be up? I mean, if you're giving a conference presentation. All right, the useful things from here. They will tell you it's between 45 seconds and a minute and a half, maybe 2, to keep a slide up. Why not longer than a minute and a half or 2? They'll tell you engineers are like cats. They like motion and they like color. But it's what you'll find out if you're for too long stuck on a slide, then you lose their attention. I mean, you need to get their attention back to what you're talking about. They'll pull out their phones and they start checking whatever is out. Why not shorter than 45 seconds? Because again, you will lose them. 45 seconds is about the time to comprehend the slide if you have something meaningful on it. So that's what sets these rules. So about a minute per slide, maybe a little bit less. Pictures are worth a lot, and every time you have a picture, you have to describe it. And the best format for a slide is to have a picture in about 2 or 3 bullet points, where each bullet point should essentially fit in a line. Why is that? Because if you don't describe the picture, if you don't walk somebody through the picture, what are they going to do? They will start reading the picture instead of listening to you. You want them to listen to you. To try to decipher your point of view. Why you want a single line bullets? Same reason. You want them quickly pick it up and get refocus on you. To try to read paragraphs and paragraphs of the slide. Also, when you're giving talks and conferences, you want these bullet points to be used for you. You should be able to speak a lot, produce 3 or 4 sentences about each of the bullet points, instead of trying to read the whole. We are told that our students are very good at presenting because we drill you. We put you through retreats and we put you, through, class presentations and stuff like that. Group meetings. I mean, all of my students, present a few times in group meetings, and everybody says, "Wow, I mean, your students are so good. I mean, they can present, they can talk." It was not always like that. When I first started off, I had a very small group, and I was not making them talk, and then they, it was this big, I present something at a conference. Oh no, what's going to happen? Presenting something in a conference is a stressful event. I can tell you. I mean, I presented something in a small conference, like 50 people. It was not a big deal. It was still a stressor. But then you go to like ISSC, and then there are like 500 people in a room, and that's a very different experience. I can tell you how I felt speaking, at ISSC for the first time. It never gets better, but you just get more used to it. They have those steps that you have to walk up on the stage. And as I got up, I was totally fine. It was cool, like a cucumber. I had my, I memorized most of the talk, but I had notes over here in my pocket, just in case. I freeze. They call me people freeze in ISSC. So I started walking up the stairs, but right when before I got to the stairs, I kind of like felt I don't have my legs below my knees. They've been cut off below my knees. So what, luckily there is a rail, so you get up over there, and even if you don't feel your legs, you can get up. I've seen people trip up going up there, and I think that must be the manifestation. They did not feel their legs. Then, you get over there and you look in the other, and the lights flare. And you don't see anybody except that it's like packed. It's like 500 people. And the only people, I had a Berkeley interview like the week after, and the only person who I saw in the audience was Bob Meyer, right in the middle of the aisle. I mean, out of 500 people over there, the only person, oh shoot, I'm gonna mess this one up. Then you go, okay, do I remember any? I don't know what is my name in here. My internet is unstable. Oh well. What's my name? I don't know. Do I remember anything of this talk? Nope. So I go with a tremor. I pull out the notes, and I put them down, and I start, time has passed, somebody introduces you, it's about 30 seconds or so. I start reading the first sentence, and then suddenly things come back and you're in the zone. And it went okay. But I've seen people stress out over class presentations. And what's the best way to stress out, to remove that stress? Practice. Don't just show up and read the slides. Practice. It's 12 minutes. You can practice it twice. It's not gonna hurt. And stick to this. Remember, and if you forget something, you have a cue. You have your 3 bullet points. You should be able to speak up for about a minute. Each of those bullet points. 20 seconds per bullet point. Describe the picture. Okay. Anybody has any questions about that? It's a lot better to have a readable schematic. Don't put something really complicated. I mean, you can do it from Cadence, but make sure to flip the colors and make it readable. If you go to conference presentations, does anybody put a Cadence screenshot now? Okay. Any other questions? I don't know. I mean, Apple will give us some prize. And I'll buy you a lunch. Everybody wants a lunch.
A question about the home solutions that we use in general. I noticed that in the homework, actually, we said in this homework we defined it as T overlap, which is the amount of time it takes data to shoot through. But then, like in lecture, we also talked about it increasing by 5%, and then that's not the same thing.
I have not looked in the solutions or the stuff. I would stick with what we have done in the lecture.
Okay. So
but we will take both, Eric solutions or this solution. It should be pretty similar. Yeah, if you apply the class solution, it should be working from the back, from filing the circle point, making clear the 5% increase. Now we also want to report a report. So the 6 pages journal form. What's a journal form? It's a 2-column with appropriate references. So let's talk about this. So now this is a complete paper. The midterm was a partial paper. Now it's a complete paper with results. So what should be your abstract? 5 sentences. Sentence 1. What is this about? What is the innovation of the state of the art. What are they trying to improve on? Sentence 3. What's the sentence 3? Your key innovation or comparison or what you're doing. What's sentence 4? Come on, we went over this. Quite proud. What is the sentence 4? What you base your results on? So this has been analyzed by, compared by simulating in EECS technology under these conditions. So we have designed this, and that, and simulated in EECS technology under these conditions. Or we have built this, and integrated in a chipyard to do that. And what's the fifth sentence? And final sentence of the option. Summary of the results, some of the key points, key nuggets. So what we have seen is that this technique that we have done, improves the delay by 30%. With modest penalty. If you listen to me and write this down, you will have a much better success with your conference papers. Whenever you write the conference papers, if you stick to the 5-sentence rules, it will serve you well. Even if you decide never to publish a conference paper, they will make you publish internal technical reports or share your technical reports in companies. If you don't want to get a PhD, you don't have to. So your master's students or bachelor students, you will go to a company and they're going to make you do both of these things, write technical reports and present design reviews. If you stick to what I just told you, things are going to go a lot better. Now, these 6 pages, what else should be there in the report? Introduction. Copy that from as much as you can in your mission report. Analysis of the current state of the art. Unless we give you strong feedback to augment that, copy that from your mission report. Then you're diving into new material, right? I mean, you should be able to recycle a lot of pages before maybe even a little more. Then you have new material, which is maybe 4 pages. Clearly describes what you've done and in this on the app. And then talks about the simulation setup, your design setup, methodology, what you've done. Then briefly note that this was done in a part, summarize that, because people will down your reports from different reviews. Summary of the results and write a meaningful conclusion. What should be the conclusion? Abstract in the past tense? No. You should restate the key results. And don't just paraphrase and restate them. There should be also a limitation. You should say, hey, we've done this, but we couldn't do it. So there are that has been left over. And finally, what is this good for? What's the utility? Make sure that you have your references, that they're properly formatted, and that you can somebody can find. Why am I saying this? Is I think it was like a year or 2 ago. I very rarely clean up my Google Scholar pop-outs, and then somewhere on the list of the of my highly cited work, somewhere, like 50 citations or something like that. There was a class project. Simply put don't put my name on file your social name. You're not the author, you're the author. So give us the accounts if you really want it, but you don't have to do it. So we put my name on that, and the paper picked up, class project report picked up citations, and it's proceedings of EV 241. Spring, I don't know, 2003 or something. It's nice, you're about to students, people will find you. And don't cite your classmates. The random people around the world. They're from your thing. So don't make it unappealing. And follow these rules. And again, you want people to know about your, it's a good thing. If somebody picks up on your work. 250 class projects have been also heavily cited because of the the use of rock and the people the class project teaches essentially what we borrowed. This class was a lot from 250 and we use a lot of people are there use rock classes. We have to say class projects. This is the documentation that's out there. Have a ton of other documentation. Does this make sense? A few other tips about writing papers. Again, practice. You use this as a practice. You get 3 of us to look at your reports and read feedback. When you're writing a conference paper, there are a few good rules of thumb, right? I mean, and she's probably not put this on a recording, but here it goes. Where do I stop reading the paper? Right. I mean, I pick up, a new issue comes, something like that, and I start scanning through it. I pick up the title. By the way, is anybody using browsing? You have a subscription to that. It's really cool. It's an online, like you get the magazine, browsing through the library. You install it on an iPad or on any iOS or Android device. You can just basically click through any journal that the university subscribes. And I don't do that now. I do that in summer when I actually have time. I need to sit down and read through the articles. Browsing. There is a way over there to log in as from an institution, and you'll pick up PDFs of entire magazines. So, if the title looks interesting, I proceed. Then what is the next thing that there will be? No, first the author's names. And credibility is important. We do want to build credibility. So if I read too many not too good papers from a particular author, I tend to stop over there and I'm demotivated. You do want to build credibility as an author. Somebody wants to read this. Then you read an abstract. And the abstract is motivated. What is the next thing that would be? Conclusion. It should make sense that if you read your paper, if you put abstract next to the conclusion, kind of close, makes sense. Same thing, if you read an abstract, introduction, and conclusion, it should make sense. And that's actually how I read it: abstract, conclusion, introduction, and then the rest. Vladimir does the same. He told me that. Any other questions? Any other useful tips?
Yeah. So I think to make it easier, these are short things. Try to make, figures take the most time to well, and they really need to be done well. Figure of certain knowledge. Right? And many people, once they scan the initial thing, they're way about how they proceed, they actually scan the figures. And they're getting a learn the figures. And then you go bother with the context around it. So you need to have a game plan. It's like almost before you start writing the rest of the thing, put a little set of sticky notes with sketches of figures. Figures need to forward the story over the line. And then you do the figures, and then the text is really writing around the figures. You're explaining what are you trying to say in the context. But try to have that tutorial view.
Yeah, perfect tip. And if you look at these short papers, ISSC and VLSI, which are basically 4 pages compressed to 2, there are about 6 key figures and 6 paragraphs describing what is in each figure. You get a little bit more in this format, 6-page format, right? A little bit about the interaction. If you are in the field of solid state circuits, there is something that has been established as a rule that to me is extremely annoying. But that's the rule of the game, is the comparison table. That comparison table towards the end of your paper, where you're supposed to compare your work to other people's work. That became like about 10 years ago, so our rule. Kind of have to have. It's a good idea to put to pick up practicing putting together tables. Why do people care about these comparison tables, and why are they, say, more important in VLSI than about any other topics? VLSI, we just went with that. Yours probably that does that. This is a nighttime job. Every night we deal with VLSI. I should not have taught that class. I should not do classes. I've learned that the hard way. Comparison papers. VLSI PPC the product. So everybody gets to review the paper, even if they're an expert in the field, if they're or not. So it has to have a project field for a technical expert in IC design. And that's where they pick up the cues on the comparison paper. Where do you stand compared to the rest of the stuff, rest of the state of the art. It just helps the original initial scoring, which paper could get discussed, which gets often checked. Once when the paper is discussed, the comparison table is out the door. It's there. The problem is the function. One thing when you read these papers, and when I ask some of you to review the papers, pay attention to these comparison tables. There are our colleagues out there who touch them, who alter the numbers, put someone else, or put stars, or other things by modifying what are the stated results. So there are the results look at. Try to get to that. And you'll be extremely pissed off if you do that to your summary. Okay. Any other questions? Is everybody comfortable with this? Practicing. I mean, many of you have not had the chance to give these presentations. Those of you that are PhD students have been made to do that. So the key thing is limit the number of slides, practice. It's a good idea if two of you split if you're doing project. Yes, just split. Nicely switch. Also, for writing, this is a good practice. Stakes are low. It's just a class project. Later on, I mean, although you start building up your reputation, if you put a really good class project, people are going to pick it up. And later on, you start building your reputation. So do it right. Okay, any other questions? Few other things, wrap up. You've covered a lot of stuff in this class. Essentially became a blend of two classes of relevant topics. And it is probably clear that how things get blended over here. We have some scenes and so on, they'll disappear over time. We talked about SOC organization and through the lectures, but more importantly, through the labs, everybody got the sense of how to build an SOC and what are the components of the SOC. We don't expect you to understand all of that, but everybody has been able to build an instance of something and simulate it. And they will try to accelerate it to that. We got the sense of other languages than plain very old 2000. We've spent a couple of lectures on technology features, and then yet another lecture on variability. Technology features are something that is really important to understand nowadays. We give you a flavor of that, but when you go to a company, usually, unless if you're in Qualcomm on Apple or Samsung, where it's clear you just need to go to the to the finest resolution. No, there is, and even there are choices. Which transistors we want to pick out there, and there was this interesting thing that I've shown on the slide that although both Apple and Huawei were had released their flagship SoCs within 2 weeks of each other in the 7-nanometer process, two processes were different because they somehow decided to pick a different flavor of the process. The number of choices is enormous now. And usually you will have a company technology guru who will do this picking for you if you're in a big company. If you're in a small company, especially if you're starting your company, it will be an interesting exercise. You'll suddenly be flooded with all these options. Not just from one foundry, but from all the foundries out there, especially if you're, you're looking at the low older node like 1016 or so, 12 to 16. So there are a lot of trade-offs, and we try to talk about those between the performance, energy, and the leakage energy. We talked about how we build standard cells and how that is going to change. We talked about design for performance, recapping and adding a little bit more on top of 151 to 51A in lab-based design. We have spent some time. We had a guest lecture and a few additional lectures about how we design memory, in particular SRAM, because that's a huge chunk of a design. And if we just apply straight to 51A design techniques on SRAM, nothing would work today. So things need to be done good. Then we spent a good chunk of our class on low power design, like what happens with lowering supplies, with dynamic voltage and frequency scaling, with leakage control, and how do we switch those points. Spent a lecture on power generation, one lecture on supply generation interactions with the plant, and that is it. We got the flavor of pretty much everything. We didn't cover stuff, many other things. There's a lot of stuff in IC design that is out there. These 5 labs, and I think next year, this energy characterization will become an official lab. We got a draft of it from there. Is there that I hope you will very much appreciate. Instead of teaching everybody here one-on-one by senior digesters how you do chips and how you do digital design flows. You've done it in class, you get the credit for that, but you've been forced to do it. Appreciate that, please. And what you'll find out, people take these labs and actually have used them to build products or prototypes inside research groups and companies. You get really nice testimonies. Or, hey, this is fantastic. I actually used to go out to set up lot 5 all this. Thank you very much. You saved me from your days. Keep them or just remember how to do it. We try to put design choices in the perspective of technology. Design constraints have changed and will be changing. This thing with the power has become probably is the most pressing thing that we are dealing with. Essentially, the power density is increasing. The amount of power that so the amount of harassment that we have in one area because of splitting of the scaling of the technology is increasing. What does that mean? In every technology generation, we have to more aggressive power management. The difference between what we can burn on a chip, what we can dissipate on a chip, and what we are able to dissipate, and what the battery can provide is more. So this is something that essentially is not power management. If you go to there is a great review of actually what we have done in this class. If you read that 200 or 300-page M1 disclaimer, somebody went and reverse engineered Apple's M1. There is about 20 pages what they reverse engineered with power management. When we cover the part of that, the default states, you can see how Apple does it. Please, user sees power management, not everything, not always the implementation that you pick up over there, the things that 10 microseconds to wake up the core. And software can measure that. I mean, many of these things are made to be completely not perceivable by the user. But there is this complex mechanism that is in there. So we focused on some of the topics. We spent time on everything design, variability, power performance, trade-offs, and power management. We did not cover things that we covered in the past. So if you discover some old exams, you will be scared. There are some pretty detailed arithmetic questions. You can do it. We trust synthesis tools nowadays. We can figure out how to do that. We didn't do domino logic whatsoever, and I used to spend like 4 lectures on domino logic and domino timing. We don't use it anymore. IO, we should figure out how to put that some more of IO back into the lectures, although it is already planned. You should definitely, I mean, if you can find a faculty, if you can hire a faculty, it would be great to teach IO. I think Vladimir is volunteering to teach an IO class, but he does, have to deal with 16B and a few other things as well. Supply generation, we have a power electronics course, so we spent a little bit on that, but there is much more. Packaging is really important. We spent more time on that. We'll need to somehow add it to the course. There are other courses that you can take. If you're a grad student here coming from some other area, not ICs, there are integrated circuits classes of interest, 240p advanced analog circuits. We most likely in the fall we'll have a data conversion class, which is 240C. Still worked out. We have a guest lecturer, and interestingly, so that would be Johan van der Hagen, who is I think now in Google. But yesterday during the, we had a Bears conference, and I ran into Bob Jewett, who is a well-known data converter person who retired. He graduated from Berkeley some 40 years ago, and he retired from KeySite a few years ago and moved back to Berkeley. This is what happens to you when you graduate from Berkeley. You go work somewhere else, but then you come back to Berkeley, which is accepted. So Bob is back and said, "Oh, what are you doing?" "Well, I don't know, billiard tables and, and stuff like that. Would you come to give a few guest lectures?" "Absolutely." So I think he'll come and tell you, if you've seen his papers, those are these crazy DACs, the arbitrary waveform generators and things like those, useful things. So this course used to be on a normal rotation, but because we have not enough faculty, the course is a special kind of offered every couple of years ago. There is an advanced RF 242, and there is advanced optics in circuit design, which this time around is a tape-out course, and we're going to try to keep that one around. If you're a grad student, if you're a PhD student, you really may not need that class because you'll have tape-out opportunities elsewhere. But if you're a master's student, it's a cool one to do, or if you're an undergrad as well. But we may have other special topics courses, like IO course, if you commence later to the high-speed ones and so on. Some of those communication systems. Also. And computer architecture, do take advanced computer architecture, and depending if you manage to hire somebody, we may have a richer offering of those classes. And then Sophia teaches machine learning hardware that does machine learning class. That has been very popular. If you are coming more from the computer architecture and would like to learn more about compute systems, do take 262. It comes, goes well with the rest. In the tape-out class, just a quick mention, last year, students in 4 weeks managed to build this. But took like lab 1 to get done. And added a Bluetooth baseband in the other, and then maybe it's accelerated. This year, we have 40 students designing 2 chips. Speaking of the field, what to look up for after that. Another interesting story from early in my career, when I came to Berkeley, which was 99, I meet again Bob Meyer, who was the senior faculty back then. And he won't be showing up, but he has some line issue. It's cool to talk to Bob. He has some line issues, so he has been deep to quarantine now because he's not supposed to get COVID if he has line issues. So, Bob said, well, glad we had a new generation of, back then there were, few senior faculty, Bob Meyer, Paul Gray, Robertson, Hodges, and others. And he said, when he was a junior faculty, there were deep discussions. What is he going to do for the rest of his career? He was hired in 1968 or 1969. Because this Moore's law was supposed to stop, in 5 years. But 1975, it was supposed to be over. So what was Bob going to do for the remainder of his career as an IC design faculty? He saw Moore's law last through his career. He, retired around 2003 or something like that, or 2004. And what he said that, well, Moore's law lasted, throughout his career and may last through your career. And I don't know if Moore's law is around. It's slowing down definitely, but I'm, like 10 years to retire. I may be proud to that point. But unless you retire in the next 10 years or so, you have a really quick startup and a quick successful IQ, it was most likely going to be gone before you retire. So that you just put it down there. If you stay on like 2-year cycles, we are down to sub 0.1 nanometers. That's subatomic stuff down there. So we have to figure out how to build CMOS with parts of an atom. We don't know how to do that yet. And as we slow down these cycles, they're still going down 0.5 nanometers. Down to 0.2 to 0.3. That's again not quite there. It's single atom devices, not CMOS. Looks like that the physics will stop, prevent us from scaling down somewhere around 2 nanometers. These 18 angstroms and stuff like that. Looks like that's about it. And economics may make those also infeasible or practical. Devices are going to look different, and we're going to have to figure out how to deal with those. So economics is playing the role now, right? I mean, there is this, what Moore's law has been an economic law all along, which basically this time scale of introducing new technologies was set by the amount of money that we put into each of these technology nodes and how much time does it take to get the money back. Electronics industry is enormous now, so even though they're putting enormous amounts of money, they can still recoup that investment in about 3 years. Not really 2 years like they used to, but they get it now back 2 years. They actually get more. You've seen what are the revenues of TSMC and lights, and TSMC in particular. It's worth $500 billion these days. As we are slowing down, we are going to look into building systems in more economic way, but also if the price is not an object in more scalable ways, we're going to see multi-chip packaging solutions. Don't worry about Moore's law. Creativity is unlimited. I mean, this canvas gets bigger and bigger every time that you get to paint up. Just think how big are your class projects? Maybe tens of thousands, I'd say 1 million transistors. If you really put your chip to all this power. What can you build with 10 billion or 100 billion or a trillion transistors? I mean, if you look at SoCs nowadays, we build Estron, and it's not that easy either. So you can have a clear, there is a lot of stuff that you can do. It's really important to keep an eye on what is going on with the technology. And many of you will go and work in leading edge companies, and you should be aware of what is happening there. But you don't have to go work with the leading edge technology. Leading edge technologies are going to be fun because they're moving from FinFETs, as I showed you before, to nanosheets, to board sheets, to these complementary FETs, and some kinds of atomic channels. These things are highly speculative. I really don't think this is going to happen. But other things are going to be super useful, like very powerful things. We're going to see that. Like, I just got another technology, please read this time. This is an opportunity. We're looking to start a company that makes, some alternative way of building standard cells from now. Get your money back very quickly. And other ideas out there for the technology. But figuring out which one of these is going to win gets you an advantage. You're seeing chiplets show up all over the place. This is a monster chiplet. I don't think it's a commercial product really showing it can be done. We have seen Apple and one Ultra. That is a fusion of 2 chips. That apparently don't run any better than a single chip, but that's a software thing at the moment. Universal chip interconnect is a standard that I think is going to most likely take off, and it will be something that is really important. if you come up with those, a way to generate those interfaces, run now, you can become quickly rich when everybody starts using and starts trying to do this. Come up with a generator of those, or a whole range of random technologies that are out there, and you'll cash it in. And back, many of these papers that we've looked in the past, turned out not to be true or right on the money, but this one was. So TC Chen's keynote from ISSCC 16 years ago was good. So he was showing, remember, this was before printed set of production. He said, that's are going to come to an end. We're going to see a printer. And yet we saw the successors. That turned out to be true. Beyond that, we're going to see subsystem integration. We are not seeing over here, he did not see enough into the future to see portions and and stuff like that. Post CMOS options were the plan C, and although a lot of people are working on that, we don't really have them. There is not much that we can do other than these nanosheet based transistors that are out there. And then there is a plan Q, which is deep down in the alphabet. It's getting to be more real, but it is not something that is going to get us into these, extend Moore's law or do anything with general computing. Although we should, that's yet another one of the topics that we should have in these classes. Now, what happens here is we try to focus on principles. We try to declutter the class from a lot of sidetracks and try to keep this focused and deliver some of the key ideas. After this class, after 251A, this class, and a few other classes that you've taken here, you have really good fundamentals. You do understand how to analyze things, and you do know that the performance of CMOS, degrades by 1%. If you lower the supply voltage by 1%, then you get 2% energy savings. So they can't sell you something that doesn't make sense, no matter what they put in the comparison. But watch out for the opportunities. Watch out for the things that really exercise these principles and make things better, encode and judge what is out there. You have the machinery in your fingers, the analytics in your fingers to analyze any paper, any idea that comes out there. But stay current. So once many of you will, go graduate with a master's degree and take off and join the industry. Make your employers allow you to go to the short courses. Some of my students are good in asking to go to short courses here and there. I say yes. Go to conferences while you're a grad student. Ask your advisors to sign you up. Now you can go virtually to any conference. There is CICC happening this week, and they have good stuff over there. I particularly like short courses over there because somebody digests these things. For me, if it is something new, it has been around for a couple of years, and I can recycle that as slides in the lectures. So try to stay on top of things. And that's it. We have a few minutes for any questions. Florian and I are here. Sophia is an NSF panel. You can fill out the course surveys, or you can just go. We are not quite done. We'll see you on Thursday this week and Thursday next week, but we're done with the lectures. Any questions? We would like to be done. If you need an extra day, we can give you an extra day. Would that help, or would that just hurt your schedule? You can turn it in early, so you can make it due next Friday morning. But that does not prevent you to turn it in early if you like. Okay. All right. There is a question here. For the previous exams, there are no useful, I mean, I have only one useful previous exam that is, where the content is not misleading. I'll post that one. That's last year's exam.